Hello, my name is Simon Goldberg and I'm a Blockchain Specialist Solutions Architect at AWS. In this video, I am going to explore how you can analyze Web3 data by utilizing the Graph protocol. I will additionally discuss the concept of subgraphs and various use cases of the graph. I will then show you how to deploy your own graph node on AWS and execute a query. Let's get started. Analyzing data originating on a blockchain can be a challenging and time-consuming process due to the complexity and variety of smart contract structures. This primary obstacle requires an in-depth understanding of the various platforms you wish to analyze. In the Web3 space, each protocol has their own way of storing and calling methods, making implementation a challenging and burdensome process. The graph helps address this issue by providing a standardized open-source platform that allows you to query data from EVM-compatible blockchains in a fast and efficient way. The primary purpose of the graph is to index, process, and store event data from a blockchain. It converts events emitted from a smart contract into entities that are consumable by a front-end or any API utilizing logic. After data is indexed from a blockchain, it is organized into a predefined schema before being persisted into a PostgreSQL database. The data can then be queried through GraphiQL endpoints on the graph node. The mappings and smart contract definitions are defined as a subgraph. Use cases of the graph protocol span multiple industries. Uniswap, a protocol in the DeFi space, uses a subgraph for fetching trading pair data in real time. This allows users to get the latest prices and liquidity information for different cryptocurrency pairs. In the NFT ecosystem, a subgraph can be created to track marketplaces such as OpenSea. This allows developers the ability to track ownership and transaction history of digital assets. Governance platforms such as Aragon use this subgraph in order to keep track of voting activities and decisions made within their DAOs. This enables a transparent and democratic process, which is crucial for maintaining trust within a community. Blockchain games such as Aavegotchi use a subgraph in order to index in-game events. The current state of the game can then be displayed on the front end. Apart from blockchain data directly, the graph can additionally query the interplanetary file system, otherwise known as IPFS, which is a decentralized network designed for storing and sharing data. These are just a few examples of how the graph's decentralized data indexing can be utilized. As innovation continues within the Web3 ecosystem, the possibilities for utilizing the graph will only continue to expand. Subgraphs can be thought of as an API endpoint that allows developers the ability to retrieve and display data in a way that makes sense for their application. Subgraph definitions specify what smart contract to index, as well as the specific events to track. The mapping is used to persist the data into the database. To fully define a subgraph, you specify three parts. The GraphQL schema defines the target schema for storage. It also defines how you can query for data later on. The mapping translates smart contract event data into entities. This component defines the transformation logic. The subgraph configuration specifies the smart contract to index, the starting block, and similar configuration data. After a subgraph has been defined, it needs to be deployed to a graph node. With the deployment, the node is aware of the subgraph and will start indexing the smart contract. It starts with the defined starting block and backfills the database up to the current block head. When the graph node is in sync with the current block head, it subscribes to future events and updates the database as they come in. In this diagram, you can see how data flows through the graph. For starters, a transaction on a smart contract will add data to the blockchain. During the transaction process, the smart contract will trigger one or more events. The graph node consistently scans the blockchain for new blocks and the data that your subgraph may contain. It will identify events related to your subgraph within these blocks and implement the mapping handlers that you have set up. This mapping, a WASM module, generates or modifies data entities that the graph node stores in response to the specified blockchain events. A dApp queries data from the graph node via the node's GraphiQL endpoint. The graph node then converts the GraphiQL request into queries for its fundamental data store to retrieve the required data. The data can then be showcased to an end user in a user interface. The graph indexes smart contract event data, which is sourced from a blockchain node. A graph node retrieves all new data for a newly created block from the blockchain node and then maps the data to the database schema. As the input source, a graph node can connect to either a full or archive blockchain node. There are several differences between a full node and an archive node that are crucial to understand when deciding which smart contracts you wish to index. A full node stores the entire blockchain's history of transactions, but only the most recent state of each smart contract, the latest 128 blocks, making it less storage intensive. An archive node retains all historical states, providing a complete historical context, but requires substantially more storage. This variation determines the data a graph node can use while constructing its dataset. In this video, I will be using Amazon Managed Blockchain to run an Ethereum full node as the data source. Let's deploy a self-hosted graph node on AWS. Before we dive into the implementation, let's briefly discuss the architecture. From the local development machine, you can directly access the Amazon Elastic Compute Cloud instance that hosts the containers. This path is used to deploy a subgraph and maintain the graph node. The graph node stores the index on an Amazon Aurora PostgreSQL compatible edition database. The IPFS node is backed by an Amazon Elastic file system in order to store the subgraph's metadata. The graph node indexes the blockchain, in this case an Ethereum full node provided by Amazon Managed Blockchain. For queries, access to the GraphiQL endpoints is routed through API Gateway and an application load balancer in order to establish stable endpoints. I will now show you how to deploy your own self-hosted graph node on the AWS. Let's get started with the prerequisite steps. If you do not have the AWS Cloud Development Kit installed, you can install it with the following command. Also, make sure that you have Docker installed on your machine. You can clone a repository from GitHub, which is linked in the description. At the top level directory of the project, run npm install to install all the required dependencies. In order to create and deploy subgraphs, you must additionally install the Graph command line interface and the Graph TypeScript library. You can install these on your machine with the following commands. Before deploying your graph node to AWS, you first need to modify the cdk.json file. The client URL specifies the RPC URL for your blockchain node. When using Managed Blockchain as your Ethereum node, make sure you're using token-based access. This is due to the default graph node being unable to generate AWS signature v4 request. The chain ID parameter specifies the chain ID of the network that we wish to index. In this case, I am indexing Ethereum mainnet, so I've set this equal to the value of 1. In order to access the graph node from your local machine, you need to open the graph node security group to the external IP address. Therefore, you need to look up your IP and modify the allowed IP variable so it gets exported to the AWS CDK as a context variable. If you're developing from an AWS-based instance, such as Cloud9, you need to open the graph security group to allow traffic from the instance's security group. If you're developing from an EC2 instance, note the security group's ID and add it to the allowed SG parameter. If you're developing locally, you can set this value to an empty string. The API key parameter sets a value that will be needed to access the API gateway for queries. This can be any string. The value of this parameter needs to be included as a header when making a request to the graph node. Now that you have completed all of the prerequisites, you can list the available AWS CDK stacks by running the following command. You can now deploy the graph service stack by running cdk deploy the graph service stack. This will create a CloudFormation template that contains all of the resources. When it asks you if you wish to deploy these changes, please enter yes. The deployment of your graph node will take approximately 30 minutes. Please feel free to pause the video and return when your deployment is ready. You will know it is ready when you see the following screen. Now that your graph node is deployed, you can create a subgraph. There are two ways to do so with this CDK application. You can start from scratch and have the graph CLI scaffold a folder for you by running the graph init command. You can also use an included subgraph as a starting point. For the sake of this video, I will be using the Bored Ape Simple example found in the subgraph folder of the repository. After creating its definition, the subgraph needs to be deployed to the node. This consists of three steps: building, creating, and deploying. The first command, GraphiQL, will build the subgraph. This will create a generated folder which has all the files which are necessary for deployment. The second command will create the subgraph on the graph node. And the third command will deploy the subgraph to the node. After the last command is finished, the subgraph has been deployed and the graph node will begin indexing from the predefined starting block. I will now run the three commands to build, create, and deploy the subgraph to the graph node. Once the build is complete, we can now create the subgraph on the node. As you can see, a subgraph has been created called BAYC example. I can now deploy the subgraph to the graph node. I first have to specify a version label to use. This is necessary if we update our subgraph and want to provide a new version. The subgraph will then be compiled and the metadata will be stored in IPFS. If everything worked correctly, it should say that the build was completed. After the subgraph has been deployed, it can be queried via GraphQL. There are two ways for accessing the graph node in this CDK application. From the local development machine, you can use the first endpoint. This endpoint also hosts the GraphQL Explorer. For general queries, from the front end or other applications, you can query the subgraph through API Gateway. There are two routes defined. The first route accepts valid subgraph names as a path element. It is used for queries on the specified subgraph. The second route is for status queries about the syncing status of your graph node. I will now go over a code example written in Python that programmatically queries the status route of the API gateway. I pass in the following query and print out the results. When I run this code, you can see that the synced status is true, and the latest block number is equal to the chain block head. This lets us know that our subgraph is fully in sync with Ethereum mainnet. You can access the GraphQL playground through the IP address of the EC2 instance by using the endpoint that I was referring to previously. I've prepared the following query that returns various information about the Bored Ape Yacht Club NFT collection. When I run this code, a request will be sent to the graph node and it will get back to us with a response. As you can see, various information about this collection has been returned. You can also experiment with the schema under the Explorer tab to help you write new queries. When you are ready to remove the AWS resources that you have created, you can run the following command. This command may take a few minutes to complete. In conclusion, the Graph protocol enables developers the ability to easily access on-chain data, and subgraphs provide an efficient way to index and query that data. The graph can significantly enhance the efficiency and performance of dApps, leading to a better user experience. That is all for today's tutorial. Thank you very much for joining me in this exploration of the Graph protocol and how you can deploy your own self-hosted graph node on the AWS. Happy development!